Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward.
This week, I think we're starting with Buildpacks, which is something I don't know what that is, but apparently there's been a fair amount of activity in it recently.
Yeah, and I've been a part of Buildpack stuff for a long time. Heroku was the inventors of Buildpacks, and so a little bit of history about Buildpacks. I think probably a lot of our listeners come from the Java world, so I'll start with context around that, where back in the day with Java, we would have containers or application servers, and what we do is we would package up our application into a jar file or war file or ear file, and we would give that to the container, and really that archive file was just a bunch of class files. But
it must have had like an interface or some sort of protocol so that the container could look at it and do something reasonable with it.
That's right. Yeah, exactly.
Okay.
So that was part of the J2E or Java EE specification, was some things around how that contract between the container and that application would interact. And so really you're just implementing APIs because you're running in the same JVM. The container is running in the JVM. It has implemented a bunch of things, and then you give it your jar file, and it knows how to take that jar file and load it and run it and all that kind of stuff.
But now we have other kinds of containerization systems.
Exactly.
So we don't really need that.
That worked well for Java and JVM stuff, but then when we started getting more polyglot, we needed something that worked outside of the JVM. And so Heroku was one of the first, when I was at Heroku, where they invented a way to essentially do containerization for user applications and run them on their infrastructure, shared infrastructure. The container was called a slug file, or is called a slug file in Heroku terminology. The container image, so that archive that you give to Heroku is called a slug file. But then the place where it runs on Heroku is LXC, which is the Linux container project. And so pretty similar to the way that we did things in the Java world. You have an image that contains the things that need to run, and then you have something that can run it. And so then, interestingly, a competitor to Heroku called .cloud invented a technology that was also similar to that, which then became Docker and is now the primary technology that we use for container-related stuff. So with Docker, you've got your container image. It's basically like tar files. And then you have the thing that runs the container, which could be Docker or it could be Kubernetes or other things like Cloud Run, Google Cloud Run, that kind of thing. So different places to actually run those container images. So similar. But when Heroku invented this containerization stuff, or didn't invent LXC, but started using LXC and giving people a way to run their applications on Heroku that can run anything. It doesn't just have to be Java, obviously. It can be anything that runs in LXC. They needed to have a standard way to convert from source code to that slug file, to that container image. And so Heroku invented what's called Buildpacks. So Buildpacks were a standard way to go from source code to that container image.
So it's kind of a build system?
So it is a way to just take your source code and compile it, if you have a compiler, and turn it into the things that can then run inside of the container. And so in the case of Heroku, they supported Buildpacks for Python, Ruby, PHP, Java, Node, then added Go and some other languages. But really what they did was they just created a standard way to do that transformation from source to that container image. And their container image was pre-Docker, so we're not talking Docker containers, we're talking slug files in the case of Heroku.
Did you have to program a special way in order to work with this?
So that was the whole idea of Buildpacks, is you take your source code and you shouldn't have to do anything. You give your source code, in the case of Heroku, to Heroku, and they're going to run the Buildpack on it to turn it into the slug file.
So any operating system calls you make are somehow translated into whatever the container is using.
Yes, exactly.
Okay.
So that's part of like the virtualization piece of the actual container runner, is where it actually will take your operating system calls and sandbox them and do whatever it needs to do. But so the build pack is that source to essentially container image process. And what happened a few years ago is that Heroku started collaborating with Pivotal, because Pivotal also used Buildpacks as part of Cloud Foundry. And they took the idea of Buildpacks and took it into the world of Docker. And so instead of compiling to a slug file or whatever it is in the Pivotal Cloud Foundry world, they changed the output format to be a container, a Docker container image.
So Heroku was working with one of their competitors.
They're not necessarily working with, because what happened was that the Docker container format became open source and became just then was standardized under something called OCI. So now it's the Docker container format.
But you said collaborated. You said Heroku was collaborating with this other company.
They collaborated with Pivotal.
Yeah, right.
Yeah. Okay. So they were essentially collaborating with a competitor. But there was benefits for them to do that.
Of course. Well, that was my point. Is that just looking at everything as competition, it doesn't necessarily produce the best results.
Well, and for user, so what had happened was Heroku had their build packs and Pivotal had their build packs, and they were different. They did different things, and so and we're producing different output formats, and so there's definitely a lot of benefit from them building common infrastructure so that they could serve each other's needs, so that they could serve their own needs, but share some foundational technology. And so that became Cloud Native Build Packs under the CNCF, the Cloud Native Computing Foundation. And so again, same goal: take source code. You shouldn't have to do anything, and it'll turn it into the container image. And so that project, Cloud Native Build Packs, has been going on for a few years. But what I wanted to get to was a cool announcement that Google made last week, is that we announced our open source Cloud Native Build Packs. And so there's the Google Cloud Build Packs now. And so what that means is that you can use Heroku's build packs with Cloud Native build packs. You can use Pivotal's build packs with Cloud Native build packs, or you can use Google Cloud's build packs with Cloud Native build packs. And I think it's actually one of the downsides of build packs is that there's not like a common shared build pack, that there are all the different build packs. But it turns out that Heroku does have slightly different needs than Google Cloud has, and so on. And so it's nice that using the same tooling, you can choose which build pack provider you want to use, but ultimately it works the same way. You give it source code, and it's going to turn it into a container image that then you can run wherever Docker containers run.
So the Google build packs are still creating Docker containers?
Yes. Yeah.
Or Docker images?
Yeah, Docker container images. Yeah.
Container images.
Yeah.
Okay, so I could use any of these and still produce a Docker container image and then run it on my Docker wherever I want to.
Yeah.
Okay, so it's making things more universal.
Yeah. Yeah.
Okay.
Yeah, and so what was interesting is that last week Google Cloud announced their build packs, but also DigitalOcean announced a new platform as a service that's also built on build packs. And then just yesterday, HashiCorp announced a new kind of platform as a service tooling suite that's also built on build packs. And so just in the last week, there's been a lot of action around build packs. And I think so the traditional way that people create their container images is that they write a Docker file, and those Docker files get pretty tedious and you have to maintain them. Whereas build packs, it's great because somebody else is taking care of figuring out the best way to go from source to a container. So no one working on a source code project should have to think about how the process of transformation from source code to a container image. And now
it's like maintaining your own compiler or whatever.
Right.
You don't want to do that.
Yeah.
So why would I choose one build pack over another?
There are some trade-offs. I don't think that there's been a lot of documentation or maybe this would be a good blog post for me to compare the different build packs. So just yesterday I was working with somebody on my team who was using build packs to take it was a Go application and turn it into a container. And when they used the Google Cloud Buildpacks, the resulting container image was like 120 megs or something like that. And when they used the, it's called Paketo Buildpacks, which are the ones that Pivotal uses, the container image was like 30 megs or something like that. And so it was clear that Paketo had done some more deeper optimizations around their process of doing this.
So size, what about performance? Is there any?
In that case, it should be the same.
Okay, it's just maybe the Google ones are sooner, so they haven't figured out how to
right. They're not as mature, so
yeah,
they haven't put as much work into the optimizations and that sort of thing. So Spring Boot now has built-in support for the Paketo Buildpacks. Actually, I think you can use any Buildpacks, but what is out of the box is the Paketo Buildpacks. So now with Spring, you say Maven or Gradle build image, and it creates a container image, and underneath the covers it's all built on top of Buildpacks to do that, because it's nice for Spring people in the Spring world to be able to easily go from source code to a container, and so they just built it into their tooling and built on top of Buildpacks. So lots of cool stuff happening around Buildpacks, and it's been fun to be part of those projects. And I built all the samples for the Google Cloud Buildpack ones, and been working with our team building our Buildpacks. So yeah, that's Buildpacks. I thought that was kind of new and exciting. And
it is. What a new world that we move into with Docker and all that stuff.
Yeah.
Actually, while we're on the subject, what is the difference between Docker and Kubernetes? I don't think we've talked about that.
Ooh, that would be an interesting one. Yeah. So Docker was really the first open source technology that standardized containers in a open source way. Whereas back to the conversation about Heroku, when Heroku did it, they had their slug file and they had their build packs, and the build packs were open source, but it wasn't a universal portable solution. What Docker did is they took those same ideas and they made them universal. So if I give you a Docker container image, you can run that thing anywhere. You can run it through Docker. You can run it through Docker on Linux, Mac, or Windows. You can run it on Kubernetes. You can run it anywhere that you can run containers. So it actually created this universal portable format that we really had with jar files and war files and ear files back in the JVM day.
But that's stuck on the JVM.
Exactly. And so what it did is it is accomplishing the same sorts of goals, but doing it in a more universal way. Because you can put whatever you want inside of your container. It's totally up to you what goes in there. So Docker was the original open source tooling to address this. They had originally started with LXC, the same thing that Heroku is using for actually running the container, but switched to another container runner technology that's more portable across platforms. Because LXC, obviously Linux, and so not as portable. LXC stands for Linux containers, and so the one that they switched to, which I'm spacing on the name of it, but is portable across platforms, which is nice.
Oh, because I thought that Docker was kind of like when you were programming to Docker, you were programming to a Linux environment.
They have recently actually added different architecture support, where now and I think it was probably Microsoft that contributed to this, but now you can actually use Docker containers with Windows being the underlying system. So the way that the virtualization is done, it doesn't actually have to be Linux. And so I don't know all the details of that, but
so it somehow knows what operating system you're programming to.
There is an API. I don't know if it's like glibc or whatever it is, but there is an underlying API that translates your syscalls to the underlying operating system syscalls, I would guess. And so as long as you can translate like Windows API calls to an underlying operating system, maybe those have to run on Windows or something like that. But the actual Docker container technology is not necessarily operating system specific.
Interesting.
Yeah.
Okay.
And I don't know all the details on that, but it really is intended to be this like universal format for sharing these things that can run inside of a container. And container being Docker, Kubernetes, that kind of thing.
Okay, and so what is Kubernetes?
Okay, so Kubernetes, a big part of Kubernetes is containers. The unit that you give Kubernetes to run is a container image, and Docker container image or OCI container image. OCI is the standardization of Docker containers. So, but you give it a container image and it's going to run it. So what Kubernetes does is Kubernetes, it's a cluster, let's put it this way. It's a higher level of abstraction over just a single Linux operating system. It abstracts across multiple systems. And so it creates this higher level where what you do is you run Kubernetes essentially on a bunch of nodes, and then you talk to Kubernetes, and kind of like you would SSH into a Linux machine. Instead, you use a tool called kubectl, which is or kubectl. It's the interface to the API of Kubernetes that's running on a cluster of machines. And what you do is you give Kubernetes a document. And that document tells Kubernetes the state that you want the cluster to be in. And then underneath the covers, what happens is Kubernetes, it looks at that document and says, okay, here's what I need to do to get to that state. I need to take this container and run it on this machine. I need to take this container and run it on this machine, so on and so forth. So it's actually doing, underneath the covers, doing a bunch of networking configuration, doing a bunch of the virtualization to run the containers, but it creates this higher level of abstraction where you say, here's the cluster state I want, and Kubernetes resolves that to actually running what you've declared.
So it sort of reminds me of like a thread pool executor. Rather than you managing all the threads yourself, you just say, here's my task, executor, run it somehow.
Yep.
So I could hand Kubernetes a bunch of different, but it still works with Docker images?
Yep. Yeah,
okay, so I could hand it a bunch of Docker images and say, here's how I want you to run these, or will it figure it out even if I don't tell it? Is it that smart, or is you have to tell it?
What you usually tell Kubernetes is, here's a container image, and here's the resources that I want you to allocate to that container image, and here's how many instances I want you to run that on. And so then Kubernetes will try to resolve that definition of the state that you want to be in based on its actual resources. So let's say that you have a node in your Kubernetes pool that has 8 gigs of RAM. And you say, all right, I want this container image to it's going to only take 2 gigs of RAM. I need to allocate 2 gigs of RAM to this container image. Well, it's going to look at that node and be like, oh, I have 8 gigs of RAM and I haven't allocated any of that. So I have space now to allocate a 2 gig of RAM chunk to this container image. So sure enough, we can do that and up and running. Now, if you have a second node and you've told Kubernetes, okay, I want this container image that's going to require 2 gigs of RAM to be run on 2 machines, then Kubernetes is going to look at its available resources and say, all right, do I have the resources? Do I have 2 nodes where I can run this container image, and do I have the available resources? And so there is obviously the chance that you're not going to have the available resources in your cluster to be able to get to that desired state, and Kubernetes is going to tell you that, say like, sorry,
can't do it at all.
Can't do it.
Okay.
Yeah. So let's say that your max instance size was 8 gigs, and you said, all right, I need 16 gigs for this container image. It's going to be like, I can't find enough resources on an instance to be able to allocate that. So it's just going to, it relays that information to you that it can't do it.
So is it only for distributing like a single container image to multiple nodes, or can you have multiple different container images and say, I mean, this one's doing database stuff.
Exactly.
You can do that.
Yeah.
Okay.
Yeah. So a typical Kubernetes cluster will run tens, hundreds, thousands of container images.
Oh my.
And the node, I think the largest number of nodes you can have in a Kubernetes cluster is like 4,000 or something like that. But that's on a single cluster, and so what large enterprises that are using Kubernetes are doing, they'll have hundreds of Kubernetes clusters, each with hundreds or thousands of nodes underneath them, and yeah, it gets pretty mind-boggling. But it's a whole lot better. Imagine if you were trying to do that scale of things by SSHing into individual machines.
I don't want to imagine that. So is there some kind of protocol for these containers to talk to each other when Kubernetes is in play?
Yes. So the protocol is just standard networking, TCP. I think you could probably do UDP networking. Underneath the covers, I think that Kubernetes is actually doing like IP tables, Linux stuff. And so it's
for speed.
Yeah. Mm-hmm. Yeah. So it's like setting up the routing for you so that containers can talk to each other with little overhead, and so, but there's a challenge there of like, how do you know the name of the machine to call? And so a big part of Kubernetes is setting up the DNS names so that you can address your containers. So, for instance, I recently deployed Kafka on a Kubernetes cluster, and so when I deployed Kafka on Kubernetes, I'm deploying a container image and telling Kubernetes to run Kafka essentially on its cluster. But then I've got an application that I also deploy on Kubernetes that's connecting to that Kafka, and so it's somewhere I need to tell my application where to call what.
Sure.
And so when I deploy Kafka onto my Kubernetes cluster, I get a name, a DNS name to address my Kafka cluster with that is determinate. So I know what that name is. So then when I configure my application to connect to Kafka, I know what name to plug in, and then Kubernetes has set up the routing and the DNS such that when my application tries to establish a connection to, let's say, Kafka, it's like kafka.local or something like that, that in Kubernetes, it knows what essentially node to call to make that work.
Yeah, it's like, well, way back in assembly language days, we had linkers.
Okay, yeah.
To resolve the addresses of things.
That's right. So Kubernetes has a network linker essentially for the stuff that's running within a cluster.
Sure, because it decides at configuration time what those addresses are, and it has to relay those back somehow.
Exactly.
Okay.
Exactly.
Yeah. Okay. Well, that
Kubernetes, the network linker, or at least one part of it is.
One part of it is that. Okay.
Yeah.
I think I understand.
Yeah. Yeah. So you would probably never use Kubernetes unless you were doing cluster stuff. Like if you're doing it, remember, like I'm still doing this, but remember like LAMP stack? It was, I've got my Linux server that's running my application. I've got my MySQL database like running on this other server. And, this was like just the easy standard way to like build a system back in the day. And you can handle a lot of traffic on a single node and, single database node, single application node. If like that's what you need, if that's sufficient for you, that kind of setup essentially, then you don't need Kubernetes. Like Kubernetes is way overkill. There's, a lot of management effort that's going to go into dealing with Kubernetes.
It's for big scaling.
It's for, yeah, exactly. But there are some nice things that it does for you, even in that smaller use case of like, if a server dies, then Kubernetes will get you back to the state that you declared. So it's going to restart your container automatically for you. It has health checks, so it'll health check to make sure that your application is responding. And if it's not, it's going to start up a new one. So it has
and Docker wouldn't do that because it's just on one node.
There is something I think called Docker Swarm that does some similar things, but most of the industry is just using Kubernetes for this kind of thing now. Mm-hmm. But yeah, generally when I'm using Docker, I'm just running it on a single node.
Okay.
Yeah. So there are some nice things even for the, like, I'm sure you experienced, like in the LAMP stack kind of days, was your server would crash and you'd have to like go restart it, whatever. And so those sorts of problems go away with Kubernetes. But there are better ways to solve those at lower scale today than going all the way to Kubernetes. Just use a platform as a service like Cloud Run or whatever, and so that you can still run your containers but don't have to deal with the complexity of Kubernetes. So yeah, I think Kubernetes is for large scale cluster stuff.
Still, okay.
Yeah.
I think I have the perspective on that now.
So one of the nice things about containers for all this is that because they're so portable, I can take my container and I can run it locally in Docker. I can run it on a managed service like Cloud Run. If for some reason I need to scale or I run into limitations with that kind of thing, then I can go to Kubernetes, and I shouldn't ever have to change my container. Like, my container is portable. And so there is, I think that's one of the big evolutions that happened with containers, is this ability to port across multiple different runtimes that actually works. Where we kind of had been promised this in the past in a variety of ways, and it never really panned out. And I think this time it's actually kind of panning out.
We're actually getting there. So could this solve, could containers solve the problem of distributing applications? I mean, this has always been a problem in Python. It's like, okay, yeah, there are ways. How do you get your Python program running on somebody else's machine when they don't have anything?
Yeah,
is that?
So you definitely can use containers for that, and people do. There is a trade-off to that, which is when you run inside of containers, it creates some complexity around the resources that container has access to and how it accesses them. So, for example, if you wanted to have your Python program read some files as part of what it's doing and output some files, that actually is a tricky thing for a container to do, because by default a container doesn't have access to the host's file system. You can mount your pieces of your local file system into a Docker container, and you can mount them as read-write, but there's all sorts of issues that crop up in that case. So I have seen people provide the option for people to like just run their let's say Python programs from a container. But I think what more people are doing is they're using Go or Rust or whatever and creating Linux, Mac, and Windows executables is the way that most people have gone for that particular use case.
I thought you said that there was another solution to this that you thought was solving that problem.
GraalVM.
Yes, that was it.
Yeah. So GraalVM does have the capabilities to produce those native executables, and people are beginning to do GraalVM based like CLI applications, because then they can write them in Java or Kotlin or Scala or whatever. And so yeah, that is something that people are doing. The Go and Rust are quite a bit more evolved for this particular use case, and so I think it's most people are reaching for Go or Rust for this today. But GraalVM is starting to get more attraction there, because it can technically do the same sorts of things, but it's kind of hard to create the Windows, Mac, and Linux executables with GraalVM, because you can't, like, as far as I know, you can't like cross-target the operating system. Like, I can't say
you have to have a Mac to produce a Mac. Yeah.
Mm-hmm. As far as I know with GraalVM, that's the case. But.
Okay. Well.
So there's some tricky things there. I think GraalVM is starting to get a little more traction around that.
Mm-hmm.
But I really like the idea of writing Kotlin CLIs and turning them into native executables. But and there's a project called Pico CLI, which makes a lot of this stuff easier around using GraalVM for CLI specific applications. So.
Oh, okay. Yeah. Well, at least people are working on the problem.
Yeah.
So.
Yeah, so containers, Kubernetes, and all that. I think there's it definitely, a lot of it is a good step in the right direction for how we distribute applications, but really for like server applications and not necessarily for CLI. So it's good to clarify that.
Yep. So, okay, I feel pretty complete with that topic. Awesome. What else are we going to talk about?
So we talked about maybe going into happy path programming and that idea a little more. We've touched on it in different episodes, but maybe good to expand on that further. Oh,
you mean just the name itself?
Yeah, like, or the idea of happy path programming. What is that idea? Right.
Yeah. Well, we sort of stumbled across the name, and it kind of stuck. But the idea of the happy path, it's funny because it's a little bit derogatory, because it's like, what it says is you go, oh, I want to solve this problem, and I'll just assume nothing goes wrong.
Assume the happy path.
And that's assuming the happy path. So nothing. I'll just program directly towards the target that I want to reach, and if stuff goes wrong, I'll just assume it won't happen, and then you end up with something which is, it might solve your problem, but it's not terribly viable to dealing with problems.
Yeah.
And so that's why when we say, oh, you're just programming down the happy path, it's a bit of a derogatory statement. But at the same time, we want to reach that. When we talk about, for example, monad-based programming, that is an example of kind of happy path programming, because I can take functions and I can compose them together without worrying about what happens between each function. And I thought, what we talked about before was really interesting, with the idea that that checked exceptions prevents you from doing composition, because you have to deal with something between each function call. So that prevents that.
Yeah. So our perspective on this is that rolling back in time, there was a lot of overhead to programming the happy path correctly, like programming for the happy path, but accounting for all the things that could go wrong. So we need a name for like the happy path, the one that accounts for the things that can go wrong. Because the evolution that we've seen is that it was really hard to program for the happy path, but with the necessary air handling. And what we've seen is, evolutionarily, it's gotten easier to program for the happy path, but deal with the things that can go wrong.
Yeah, because it used to be that if you programmed down the happy path and you didn't deal with anything, you would get, like, on Windows, the blue screen. It would just freeze your machine. It would do, and it's like, well, and then we introduced exceptions, and at least when that happened, you'd get some kind of message that something went wrong, and the program would end, and it wouldn't take down the entire operating system. So it was better. It was still not great if you didn't do anything except let the exceptions get thrown. If you didn't, maybe, and then, as we've discussed, most exceptions can't be recovered from. There's a few. Turns out a small handful, which is a problem with the exception handling theory, is that because it was kind of based on the idea of, well, we want to be able to recover from these things. Well, and if you can't recover from most of these things, then that sort of brings that into question.
Yeah. Yeah. So part of the way I look at this is, it's like, how yucky does it feel to ignore the air conditions that may happen, the unexpected things? How yucky does it feel? And in the case of exceptions, it didn't really feel that yucky. Like, I would, I'd have to put in a try catch. Maybe I would put in a try catch if
you were forced to.
Right. But even if in my catch block I was just like, log this error or ignore it, or what? Like, how many times have you seen in a catch block // ignore this error, it'll never happen, or something like that? And like, that didn't feel that yucky. And then Go came around and they did like the tuple return type, where you on the left side get the value, the right side get the error, or something like that.
But it's still optional. The programmer still has to.
Yeah, and you see in a lot of Go code, if error, ignore basically.
Shrug.
Shrug. And so it didn't feel that yucky to like ignore the possible error states. And then
when you say it didn't feel that yucky, you meant as a programmer you could go, I'll just ignore this for now and I'll come back. If it's a problem, I'll come back and deal with it.
Yeah,
that's
just
what you
like,
meant.
I don't feel shame around letting that code ignore the possible things that could
And you're
go wrong.
saying you should feel shame.
I think you should feel shame. Okay. Or maybe the programming models should make it easy for you to program on the happy path so that you don't have to feel shame or anything. Mm-hmm. It just is so easy to account for the error conditions that you don't have to feel yucky, you don't have to feel shame. You just do it because it's easy. You program the happy path that accounts for errors because it's easy.
I see. So what you're talking about is making the happy path the one that takes care of errors.
That's right.
Right.
Being able to program the happy path, but also account for the possible things that could go wrong.
And what Cedric was saying was that one way to do that is using monads. One way to do that is using the Kotlin approach of returning null or a value. And so there's a spectrum of approaches you can take to doing that.
Yeah. And so in Scala, or really any language that has like kind of ADT, algebraic data type support, where I can say this function is going to return either an error or a value.
And that's built into the language to be able to say that. Because of the ADT.
You can do it without the ADTs.
So, right. I mean, Go effectively does that.
Yeah. If you have inheritance, then you can model an either, which is a ADT sum type. Mm-hmm. So you can model that with inheritance. It's just not quite as convenient. I
think you could use generics to do it too, right? I thought I had seen it.
Yeah, maybe.
Generics. Yeah. Okay.
But when your type system actually conveys that back to you as the caller, then it becomes easier to, especially if you have like good pattern matching, then it becomes easier to pattern match on that thing. And you can still ignore the possibility that it can fail. But when it's in the type system, for me, when it's encoded like that as a either, it feels really bad to just like toss out that.
I'm just going to ignore this. Well, I think it's what checked exceptions were intended to do.
Yeah.
I mean, initially in C++, exception specifications were supposed to help you do that, and then Java went one step further and said, "No, we'll force you to do that."
Yeah. And so, in some ways, this programming model is like checked exceptions, where the possible error states are explicit. And it requires the developer. So like in the case of, I don't think it's the default, but in the case of both Kotlin and Scala, if you pattern match on essentially a sum type, a ADT sum type, and you don't account for all of the possible conditions, then the compiler, I think by default with both Scala and Kotlin, it gives you a warning, but you can tell it to turn that warning into an error so that it actually won't compile unless you, in your pattern match, have actually handled all of the possible ones. Yes, you can handle it and still ignore it. That is a possibility, but that's where the yuckiness factor comes in, is that it should feel pretty yucky to the developer to say, yes, I recognize that this thing could fail and I don't care. Like that should feel pretty yucky.
You're forced to explicitly say you don't care. Rust has a function which I didn't realize that like Go didn't have an equivalent of this, or maybe it doesn't. I didn't know about it, but they have something called unwrap because they return this package of information, and if you want to get the data out, you can call unwrap, which I think if it's a failure, it throws an exception. Otherwise, it returns the value. So it's kind of the shortcut, or in a sense, the I don't care.
Yeah.
But you see those, and you go, okay.
And I think the compiler like tells you like, hey, this is unsafe, or this, you know, you should probably do some better stuff here. So the sum types I think are a good evolution in this direction. Monads are, I think, the even better way to deal with this, because with monads, it's easier to chain together operations and stay on that happy path, but also be able to easily account for when things go wrong. And this is because if you call flat map on something that is either an error or value, that thing is only going to happen if you're on the happy path. But then ultimately you're chaining together that sum type of this thing can succeed or this thing can fail. And so you can be chaining your happy path, like this work, this work, this work, this work. But then ultimately that the thing that you get at the end of that is still wrapped into something that can either succeed or fail.
And I think Cedric's argument was that yes, but there's a significant amount of overhead to achieve that.
Yeah, he was talking about the lack of universal composability of monads, I think is what it was, and that whole like chaining these monads together and staying on the happy path. It works well if all of your monads are the same type. They're all futures, or they're all options, or whatever. But as soon as you start mixing and matching futures and options, or whatever it may be, different monads, then you run into some complexity, and you have to think about how to deal with that. And then you get into monad transformers, and so So does that? I mean, it sounds like that happens enough that you need a thing called a monad transformer. I don't use monad transformers.
Okay. See, now, because this is what we were talking about at coffee, is like, are we solving a problem that doesn't, like my example of a list of cats and putting a dog in it, and, that would be terrible, but how often does it happen, and how hard is it to see it when it does?
Yeah.
Maybe this is a situation where...
Yeah, I run into this so infrequently that I do basically... manual monad transformers.
So, but the mathematicians would want to include that to be complete for them, even though it may not be a problem that we actually have to solve.
Right.
So it's like, okay.
Yeah. It's so, to Cedric's point, it's not, monad transformers are not something that everyone needs to reach for. Most of the time when I'm doing composition of stuff, I am actually composing the same type of thing. And so it's not an issue. It's like, I'm composing futures with other futures, and so they obviously do compose because they're...
And that sort of makes sense that you would compose something that would be dealing with the same type.
Right.
So
I'm not saying I never have had to compose like options and futures, but it's happened so infrequently for me, and I'm able to do it so easy manually that I haven't had to reach for general monad transformers.
See, well, that's an interesting data point then.
Yeah. But ultimately, what for me, monads have helped me program the happy path, but actually doing the explicit error handling. And I at this point can't imagine going back to like tuple return types or exceptions or any of the more kind of primitive ways that we dealt with happy path programming. It just, for me, it has made my programs much more robust with dealing with error conditions. Like I have a number of applications built on this paradigm running in production that have run for years and never had a runtime exception, never had a condition that wasn't handled
nothing unexpected.
Unexpected, yeah. Yeah, exactly. And it was not a lot of cognitive or programming overhead to be able to do that. But I did have to learn monads.
Well, maybe we've gotten a little closer in explaining them.
Yeah. So So I think on this podcast, I hope that we continue to weave in the idea of happy path programming and talk about the different ways that it impacts all sorts of different things. Like we talked about the builder pattern with Cedric, and I've had a lot of Twitter conversations about the builder pattern. And for me, like builder pattern, it's not helping you stay on the happy path in the way that I would want.
Well, before you completely dive into the builder pattern, which I know you want to do.
No, we don't. We need to go back. We've talked about the builder pattern like way too many times.
We have. Because to me, the idea of the happy path is not limited to that, because I just think of it as, in general, higher level concepts.
Yeah.
And so you're able to use this concept and program more effectively rather than some of the lower level languages that we've had before. I've always wanted to crawl up that ladder to higher level concepts and being able to do things more powerfully. So that's the general idea. I think this, how do we compose functions is a specific instance of that.
That's right. Yeah.
And I think that is why I keep getting drawn back into Python, because it's not just the, flavor of it, but it has so many, solved problems out there that I can find by just doing a pip install and looking at, that's a good example, because when you get a library, usually the easiest thing that you find to do is the thing that works.
Yeah.
And so that's probably what keeps drawing me back to it. It's like, I could solve this problem in some other system, but it would be harder, probably.
Yeah.
And it would be happier and easier to do in this case.
Yeah.
So,
yeah.
So, but there's definitely higher level languages that we haven't imagined yet.
That's right. Yeah.
So we're getting there.
That I think, like we've said, the higher level languages continue to make the happy path, the real happy path, where you are accounting for the air conditions, easier to
conditions and all the other things. Yeah. I mean, it's not. What I mean is, it's not limited to that. But we had our friend Jeremy Cerise came for a developer retreat, and that's this thing that we do here occasionally, which is people show up, and it's usually a small handful of people, like no more than, I don't know if we've had any more than 8, so it's very small and intimate. And we work on a problem which is usually kind of ill-defined. And so part of the process is just to kind of wander around and discover what problem we all want to solve. And in this case, Jeremy said he had been here during the Winter Tech Forum, and we all came down with COVID, so we felt that we probably weren't going to cause problems in that way. And so he wanted to investigate Rust further. And so we did. And we had tried this a couple of years ago, and I came away with kind of a bad taste in my mouth. And so he wanted to revisit it. So we did. And I have to say, it was a much better experience than my first encounter with it. But I did come away realizing that, okay, this is what I would call a very high-level assembly language, which is, I know, 2 really extreme ideas, but it really felt like I would so much rather do it if you were saying, well, use assembly language or some very low-level approach, C for that matter, or use Rust. I would go, okay, for that problem, I would probably be willing to go through and figure out all the ins and outs of Rust, because it's like a super powerful assembly language is kind of what it felt like to me. But like one of the things in the book, and I have to say the Rust book is amazingly well written and very insightful, and I got some really good new ideas from just the scanning of it that I did. But they say in the Rust book that ownership is the primary concept in Rust, and that's a really interesting place to plant your flag. But it also says that, we're dealing with super low level stuff here. And if that's not what you need, this isn't the right language for you. But one of the things that we kind of wandered around for a while figuring out what problem we wanted to solve. But eventually, both Jeremy and I have a lot of background in Python. And so we decided to look at, well, what would it be like to create a Python extension using Rust? And we ran into issues here and there until we discovered this library called PY03, and I think it's something like Pythonium trioxide or something. It's with Rust, they're always looking at oxidation and things like that because that's what Rust is. Right. So, but this thing basically would pop out the framework for a Rust extension for Python, and from Python it would just look like import module, use module, like it was just a regular Python module. But at the Rust end, it was all worked out so that you could write your Rust code and it would just be totally right to the metal.
Yeah.
And so from an efficiency standpoint, I would say, like, if you're running into speed issues, this might be, because I've looked at the various different, people have been trying to solve this problem from the beginning. I was like, how do you make it easy to write C extensions, C++ extensions, anything that...
There are times that you need to go down to the metal and
somehow make it faster.
Make that easy.
Yeah, and this, I have to say, well, you're probably not going to get any closer to the metal and probably not have an easier time like setting up this module and getting it to work. So I have to say that was pretty impressive.
Yeah.
And then we also looked at using Go, because Jeremy had a lot of experience using Go and he didn't want to quite give that up yet. Because, it has some benefits. Like if you're doing concurrency stuff, it's pretty sweet. It's pretty transparent. You just
for some use cases of
yes, of course. As with all concurrency, it's like for certain class of problems, but a pretty good sized class of problems, I would say. So, and then we didn't find anything like what Rust had done with this PY03, but I remembered gRPC, so we started looking into that, and there's some really nice setups for connecting from Python to Go using gRPC. Yeah. So that was...
So before we go into a little bit of gRPC stuff, I haven't done any Rust. I've looked at some code, and even though it is very low level, it seems like they've actually embraced some pretty modern programming paradigms like type classes. Type classes are fully supported. I forget what they actually call them in Rust. They have a different name. But type classes are just supported and
invariants and lambdas and it has a lot of higher level concepts, but all designed around, you always have that metallic taste in your mouth when you're working with Rust. It's like, you're right next to the metal.
Yeah.
And it's really impressive that way. I have to say, I'm much more interested and there's a whole bunch of fascinating things about it. The ownership thing, which isn't just for managing memory without a garbage collector. That's the other way that you could look at it. You want to do these things, but you don't want to have you don't want the overhead or uncertainty of a garbage collector. Then it solves that problem. But then there's the ownership also works well with concurrency issues. And so it protects you from a whole bunch of things that...
Remember our explorations into Ponylang a while back? And they have a similar model of making the ownership very explicit. And they're based on the actor model. But yeah, it's interesting that both Rust and Pony, two pretty modern languages, have both, from very different kind of perspectives and levels of abstraction, and have both embraced the explicit ownership as a core piece of the language.
Yeah, well, and the more recent versions of C++ with their smart pointers and shared pointers, I think, they have adapted that and then made that the issue of memory management much easier.
Yeah.
So
Anyway, fascinating. So back to gRPC. So I've been pretty involved in gRPC Kotlin in that project, and I think there's a lot of interesting things to gRPC as a protocol for communicating across networks. One of the underpinnings of gRPC is protobufs, which is the compact format for serializing stuff. But the kind of great thing about protobufs is that you have that IDL where you define the structure of your messages.
Interface description language.
Thank you. Mm-hmm. And then protobufs can then generate many different languages that can read and write the same protobuf. So you get really great interoperability across languages, which is a really cool thing. So then gRPC adds the networking piece on top of that. So you get really high performance HTTP2 based networking with protobufs as the serialization format. So yeah, I think there is a lot of interesting pieces to gRPC, and a lot of it. You and I have always looked for like what's kind of the easy way to build distributed systems, and it feels like gRPC
multi-language systems.
Yeah, and multi-language systems, and it feels like gRPC is a step in a good direction there. It's not quite the what do they call it, panacea that Unison is, but Unison's out a bit further. For today, gRPC is probably a great option.
Yeah, but you can, you talked about network systems, but it can also be within a single application. You can, like, this is what we were looking at it for. It's like, okay, I'm running Python, but I want to do something that works better in Go. So I can use gRPC to call.
As the, what's the name for the function, foreign
remote
function?
Procedure call.
Yeah, but you have essentially two different processes. So it may be running on the same machine, so it doesn't necessarily have to go over a network, but you do need to serialize in a standard format that can be read and written on both sides and that sort of thing. So, as a RPC framework. Yeah, gRPC is what, Google RPC or something like that.
I assume they never explicitly said G is for Google. I think you're just supposed to guess.
Yeah.
So, and that's my interest, is like, how do we, some languages do things really well, and some languages do other things really well. And I've always been fascinated with this idea of being able to say, well, you do this good, let's use you for that, and you do this good, and let's use you for that. And then
how do we bridge those?
Right, how do we bridge those? And then so we found this PyO3 thing for Rust, and then gRPC seems like, the video we watched said that Google itself runs billions of gRPC calls per second. And so probably pretty well optimized. And that's the one thing we haven't gotten to quite yet, is just a simple comparison between, say, calling a Python function a million times and calling a gRPC function that does the same thing a million times.
What's the overhead of the serialization and deserialization and all that? So, interesting.
I'm guessing it's pretty efficient just from the standpoint. Well, for one thing, like every time you say serialization, I get this little, but it's not, because you've got this packet of information. It's not going out like the way I've always, serial. Yeah. It's like, serial port was like, here's the thing, here's the thing, here's the thing, here's the thing. And then you go, okay, I got it all at this end, and now I can do something.
Yeah.
Whereas this is like, no, this is just a format where I'm handing you a packet of data, and it's all really packed together efficiently. Yep. It's just that one packet, and then that makes the call. So it doesn't feel exactly like what I've always thought of as serialization.
Turning objects into byte representations.
Mm-hmm. Right.
Yeah.
Right. But much more compact than at least traditional serialization.
Yes. Yeah, and I'm way more compact than JSON or all the other.
Well, like XML RPC was one that it would work, but I wouldn't want to do too heavy of a load on it.
Yeah. I think I was telling you about, recite it for the podcast, about how back in the Java EE, J2EE days, JBoss was Mark Fleury was presenting about JBoss at the Denver Java user group, and I remembered something that he said. It's really stuck with me, because he was talking about how in EJB worlds, you, as a developer, you could either program to the local interface for an EJB or the remote interface for EJB. And it was up to you, the developer, to make that decision. Is this thing running in the container where I am, and I can just call it via in-memory call? Or is it running on a remote machine and I need to do the serialization and deserialization? Right, like you as a developer have to understand network topology, the deployment network topology, which is just silly, right?
Well, because you would probably want to change that at times.
That's right, yeah, and it could be dynamic, right?
Right.
And so if you're programmed into the local interface and all of a sudden somebody split the thing that you're calling out to another machine, your code's going to break, right? And so it was a bad idea, but what ended up happening is that everyone started just programming to the remote interface because they weren't sure about
guaranteed.
The network. Exactly, it's going to work. Mm-hmm. And so the containers, what they would do is let's say your two AGBs that you're talking were running in the same container. If you're doing a remote call, it's going to go through all the XML serialization stuff.
Because they were using XML?
Yeah. I think that was like the standard serialization for most containers. I think containers could implement it differently, but
XML was the universal solution at the time.
That's right. So if your two AGBs are running in the same container, it's still going to do all this serialization and deserialization. And so Mark Fleury, he was like, JBoss is so much faster than everybody else because as a container, if we see that you're making a remote EJB call and we have the being in the local container, we just do the in-memory call instead of doing all the unnecessary serialization and deserialization. And all of a sudden, JBoss, if you're making a local call but you define it as a remote call, it can optimize that for you and make it in memory, which is 1,000 times faster or whatever. And so it always stuck with me that a lot of times we program for a network, a distributed system. And in the case of gRPC, we're programming for a distributed system with serialization and deserialization. And yeah, that serialization and deserialization is a whole lot faster than XML and all that kind of stuff. But wouldn't it be nice to have a programming model where we as the developer don't have to make the decision and the environment knows what to do?
See, I was kind of imagining that gRPC worked that way, and you're telling me it's not.
As far as I know, it doesn't. But
I mean, it could.
It could.
It could because it's just oh, I see you're doing this. I'll rewire that for you.
Yep. Yeah. I think it could. I don't know if it does, but
yeah. Well,
but
don't you
Unison,
work at a company where you could find it out?
That's right. I could go find that out. Unison, I think, has the best opportunity to actually give us the future that we want around decoupling our programming from network topologies. Because with Unison, everything is a function with a hash. And so that function with a hash, you don't care if it's in the local machine or if you have to serialize and go over a network, whatever. It is just a function with a hash that you should be able to. And I would hope that at some point Unison is able to help the thing that's running your program make the decision around, do I do this locally or do I do this remotely? Then all of a sudden you get transparent distribution of your application where something can be making the decisions for you around, should I run this somewhere else or should I run this here?
Well, yeah, I could imagine a dispatcher. If for some reason it makes me think of Julia, because the first time you call a Julia function, it compiles it down to native code, and then the next time you're just calling the native code. So if you made a call, and the first time you made the call, the dispatcher said, oh, this is local, this is remote, this is maybe other decisions it makes.
Yeah.
And then it says, oh, it's local, so I'll just wire you to that. And then your call now from then on just becomes that direct call.
Yep.
Or if it's remote, it does something else.
Yep.
Yeah, it doesn't seem that. I mean, as long as you have that concept.
It seems plausible,
dispatcher. Right? Yeah. It seems like.
I think this is the ultimate direction that Unison is heading, and a reason for some of their design decisions. But we should get one of the Unison folks on our podcast. That'd be cool.
There you go. Yeah, so you've looked at the language, right?
I've looked at it and played with it just a tiny bit.
And what does the syntax look like?
It's functional syntax.
Does it look like Haskell, or does it look like... Like how functional does it?
Well, I haven't done Haskell, so I don't know. It's very functional.
Okay.
Yeah, it's very functional. And it was a while ago that I played with Unison, so I don't have a good clear memory on what all it was like. But I need to play with it more, and we should get Runar, somebody from somebody from Unison on to talk more about it, because every time I hear one of them talk about it, I'm just like, oh my God, this is the future. I'm just enamored with what they're doing. So yeah. But gRPC, did you have anything else on your experiences with gRPC?
No, I think that's about as far as we got. It just looks really promising as a way to call out from Python to other languages.
Yeah.
Which, again, my interest is...
Inter-process communication protocol.
Yeah. It seems like it has a lot of promise there.
Yeah.
So, but we're still, like Jeremy's working on an example to test it out.
Benchmark.
And the interface description language is... I found it very intuitive, and it's not overreaching, because when we... initially, when I was on the C++ standards committee, we started, there was a parallel thing that went on, which was Corba, Common Object Request Broker Architecture. I mean, the name itself is complicated. And then there was the committee for it, which was I don't remember the name of it, but it required a lot of, it was just so... It was committee first design, basically. And you had a bunch of competing companies on this committee who wanted their things in. And so there was a whole bunch of that. And as a result, we didn't have... I mean, we had an IDL, but there wasn't like the tools to take the IDL and generate things with it. That wasn't... So you had to do a lot of stuff.
Conversation about declarative languages. It's like... So many times it's like, oh, the tools will be great and it's going to be awesome, and then the great tools never come, and so you're just stuck with this terrible IDL.
Eventually, they got there,
tools.
But
around Corba,
Corba, I guess. But I think everybody had pretty much moved on by that time. Whereas my experience with gRPC is like, oh, here's the IDL. It's not very complicated. It's not trying to do all the things. I can't even remember all the things that Corba was trying to do. It's not trying to do all those things. You just write this, it generates code for you, and you write some other stuff and it works. So it's like much more accessible, I think. It seems to have a lot of promise. So I would definitely look into that if I was having either performance or... Well, most of the time it would be performance issues, even if you're looking at concurrency issues. Generally that's going to be a performance. In fact, if you're doing concurrency that isn't trying to solve a performance problem, then I would say rethink your life.
That's just making things hard for no reason.
Yes, exactly.
All right.
Yeah.
Thanks for listening.